Hello everyone. Sorry for the delay. And welcome to the network seminar series hosted by the Center for Network Intelligence at BCE and RBCCPS at ASC. It's my pleasure to introduce today's speaker, Professor Thirupathaiah Vasantam, and he will be speaking on optimal scheduling in a quantum switch, capacity and throughput optimality. Thirupathaiah Vasantam is an assistant professor at the Computer Science at Durham University, UK. Before that, he worked as a postdoc in the College of Information and Computer Sciences at the University of Massachusetts, Amherst, USA. He received his PhD from the Department of Electrical and Computer Engineering at the University of Waterloo, Canada, in November 2019. He obtained his bachelor's and master's degrees in engineering from Osmania and Indian Institute of Science, Bangalore, respectively. His research focuses on stochastic modeling and performance analysis of communication networks that have applications in quantum networking, cloud computing, and Internet of Things. Audience is encouraged to ask questions at any point in the talk. For those attending online, questions may be asked either by unmuting and speaking directly or typing them in the chat box, from where they will be related to the speaker. Over to you, Professor.
Thank you so much for the introduction. Firstly, I would like to thank Professor for organizing this and also the support team for everything. So today I'm going to talk about optimal scheduling in quantum switches. This is a joint work with our postdoc Sandra Bombay and my colleague Neil Walton, who is a professor of operations research in the Durham Institute. This research is funded by Informed AI Hub. I will give a quick. This is not working. Okay. So here is the quick introduction to Informed AI Hub. So Informed AI Hub is one of the three hubs which are funded by EPSRC. Okay, these hubs focuses on mathematical foundations of artificial intelligence. Basically, we focus on design and analysis of AI algorithms and their applications to various networks that have distributed and heterogeneous agents. For example, in this hub, we work on quantum internet at Durham, and other universities work on communications, machine learning, robotics, etc. So there are several postdoc positions available. If any of these students are interested, you can contact relevant people in this hub. So here is the outline. So first I will begin with some basics on quantum networking and quantum mechanics. And then I will discuss switching architectures, both practical and quantum switches. And I will discuss what are the differences between them. Finally, I will discuss what is the capacity region of quantum switch and how do we develop throughput optimal algorithms for quantum switches. Okay. So here is the objective of this work. So we have a quantum switch, which is a quantum device in the middle. And for example, we have three users, 1 and 2 and 3. And the goal of the system is to distribute entanglements between different user pairs. For example, it can be between 1 and 2. Okay. So for now, assume that entanglements are essentially coupled to qubits. Okay. For most of the applications of quantum, we require distribution of entanglements. Okay. So in practice, we can connect different users to the switch via fiber optic cables. And if the distance between the users and the switches are sufficiently small, with high probabilities, we can create entanglements between them using direct estimates. And then the switch has to combine the link-level entanglements to create end-to-end entanglements for different user bases. For example, if you want to create an entanglement for user 1 and user 2, we need to combine entanglement of this link and another entanglement of this link. So basically, the switch combines them by applying some quantum operations at the switch using certain quantum devices. Okay. And across links, we create link-level entanglements continuously, for example, with some rate lambda L. And every link can only store up to B link-level entanglements. There is some quantum memories across at the switches and users. They can store only up to B link-level entanglements. And then these link-level entanglements expire with some problems in every time slot. So quantum bits are fragile, so they easily interact with the environment, and if there is any noise in quantum device, they cannot be used further. Okay, so we assume that these link-level entanglements expire with some properties in our structure. So now if you take a quantum switch, it is essentially a two-sided queuing model. So on one side, we have different applications that are generating requests for creating entanglements. For example, this is a type 1 request, which is asking for entanglements between user 1 and 2. Okay, and this is a type 4 request, which is asking for entanglements between 1, 2, and 3. So we can also create multi-qubit entanglement. For example, type 4 request is a type of 3-qubit entanglement. Okay. So on one side, we have requests coming into the system, and then they are stored in XCFS queues. On the other side, we have generating link-level entanglements, which are stored in quantum memories. And the goal is to match these link-level entanglements to different requests, different types of requests. And every type of request is arriving at rate lambda if the type of request is okay. Now our objective is to distribute entanglements in a quantum space in such a way that the request queues are stable. So okay, so we want to find an optimal policy so that we distribute entanglements optimal in such a way that the request queues are stable. Okay. So here, when I say optimality, it is through optimality, meaning that if there is a set of rates, request rates, that can be stabilized under any policy. We want to come up with some policy that also stabilizes all feasible rates.
So I didn't quite understand the model. So you have this memory, right? Quantum memory for storing entanglement, right? So once you come in with rate lambda and says quantum, I don't know what you're saying. Yeah. So one entanglement is created and stored in Z3 for that request. Is that true?
Yeah.
Okay, and then this Q4 is the request for different type of entanglement. So suppose I mash lambda R1 to 1 and 2, like the Q1 and Q3, right? The link 1 and link 3. Link 2.
Yeah.
That's what we're gonna do, right?
Yeah.
So what does that mean? It means that I can remove one request and I'm gonna remove one from memory. Is that what?
Yeah. So suppose if you are serving one request for type 1 request, it means that at the end of service you will remove one request here and one link-level entanglements from here and one link-level entanglements from here.
Okay.
Sometimes this matching is failure. Even if the matching fails, still we need to remove these qubits from memories because once they are used for operations, they will be destroyed. So they cannot be used for future requests. Okay. So this is our model. This is our objective.
Sorry, but I didn't understand. You said when its use is destroyed, when else it is destroyed?
So this matching that I mentioned, the quantum switches apply some operations. Those operations are not always successful. They succeed only with some.
So even if you do a bad matching, they will still be wrong.
Yeah, so they will be almost remote. So this side, if you use qubits, they will be always remote from Q.
But in your model right now, you're saying whenever I match up, it's not very important.
No, I'm assuming that they are probabilistically successful.
Oh, okay. Got it.
So it is essentially a two-sided queuing problem.
So in general, why would you not be successful? Because you're saying there is some uncertainty in finding matching process.
So when you play with these qubits, their giant state should have some properties.
Okay.
And that giant state will have required properties only with some probabilities.
So,
otherwise, they will not have required properties. Okay. So
why another question?
So here like Q1 and Q2 both want to match with C1, right?
Yeah, so Q1 requires one qubit from here, one entanglement from here, one entanglement from secondly. Q2 requires one entanglement from 1 and another entanglement from 3. So there is a competition for entanglements of link 1 by both these requests. So we need to resolve competitions among requests.
Can both of them? If they had two, they could have got one each, right?
Yeah, they can get one. Also, in practice, quantum switches will have limited device. That will also enforce some classification. How many you can match? So for this model, we have that as long as there are some LLEs on this side, and set quantum switch can match it.
This is more questions.
Yeah, so if you have, but the matching algorithm does not restrict how many you can match. Like one can, Q1, both can match with.
Match as long as there are enough LLEs, enough entanglement. But in practical systems, there will be constraints. that will come from a quantum switch. We have not considered in this case, but that will be a simple extension.
Your goal is to keep those queues stable.
Stables.
Sir, if both queues, like if the request comes from both queues, which one will it send the request to?
So that is the question. So how will you make decisions? So there is now for example, type 1 and type 2 requests, they require entanglements of link 1. So how do you allocate these entanglements of link 1 so that these two queues are stable? Okay. So the scheduling algorithm has to consider the queue size of these queues as well as queue size of these resources. So essentially the left side queue is a resource system, servers, and the right side queue is the application that are generating requests.
Left side is in some sense bounded, right? Because
Yeah.
there is not really a queue. Queue is only on the right hand side.
Yes, but although it's a finite queue, but they still control the service.
I agree. So
Yeah.
if you don't have enough, your service get impacted. But there's no
Yeah.
stability on the left hand side. That is more about how bad this is, so that will disappear.
Yeah. So suppose this B becomes smaller, then you cannot solve these requests. As B increases, you will solve more and more requests.
So the link level entanglement, even if it gets created, it is peaceful, then it's just wasted. You don't know where to store it.
So this Prof, even if there are entanglements, there are already B, then you cannot store it, so you will throw it away.
Sorry, so this be.
So B is the memory side, how many you can store. So on every link you can store only 2 link level entanglements. Okay. So this is the objective. So now I will give a quick introduction to quantum networking physics. So why we need to study quantum networking? So here is the following reason. So as the transistor size has increased over the years, we were able to place more and more transistors in a single chip. Therefore, our computational power has increased. Now, if transistor size increases further, their size will be similar to atomic size. So now the correct theory for understanding atoms is quantum mechanics. Okay, so classical mechanics is a good approximation theory for large systems like humans, vehicles, and so on. But for small particles, we need to use quantum mechanics.
They're not hearing. They won't hear. Are you able to hear this on your phone? So it's not audible. You can go outside.
Okay. So therefore we need to come up with quantum devices that work based on quantum mechanics. Okay. So in 1981, in a seminar, Richard Feynman has suggested that if you want to understand nature, or for example, simulate the different physics particles or molecules, different proteins and so on, we need to use quantum computers because the nature follows quantum mechanics. Therefore, the computer allows you to have quantum mechanical properties. And further, the classical computers will not have enough computational power to exactly characterize the behavior of small particles. So that was his conjecture. And immediately after his comment, in 1984, there was a breakthrough result, which is that people were able to come up with the BT84 protocol in Albia, which is essentially a QQD protocol. And the main advantage of this is that if some eavesdropper tries to copy quantum keys, then the eavesdropper can be detected with almost 1 probability. Okay, so it's very high secure. And then in 1994, Twitter has showed that large integers can be factorized using quantum computers in polynomial time. And we use this property, factoring of large integers in current cryptographic systems. And our assumption is that classical computers, even supercomputers, cannot find computers for large integers. So that was the main assumption. And Twitter showed that quantum computers can break that result in polynomial time. So therefore, all current cryptographic systems will not be secure if someone has access to quantum computer. So that was another important result. And then in 2016, China has done some satellite experiment where they showed that they can distribute quantum keys using satellites. And the distance between the source and destination node was around 1200 kilometers. So over large distances, their experiments showed that we can distribute quantum information. So after this result, several countries and several researchers have shown interest in this technology. Okay, so after this, the research and this field in this topic has increased. So what is qubit, right? Basically, okay. So qubit is if you take a classical bit either is a 0 or 1, for example, switch on, switch off. Whereas quantum bit represents a superposition of 0 and 1. For example, in practice, we can prepare a qubit using the spin of an electron or polarization of photon, and then there is other properties of atoms. And essentially, a quantum bit is a superposition of 0 and 1. Okay. So mathematically, okay, so this is the definition of qubit, and so in practice, we can use different types of qubits. For example, for communication, that is, if you want to send quantum information from one quantum node to another quantum node, photons are good properties for communication. Okay, for example, because they will transport over fiber channels, so they can travel for over long distances. And for storage and computation in quantum computing processing units, we generally use different type of qubits. For example, trap balance, nitrogen vacation centers in diamond, superconducting qubits, etc. For example, all the startups, every startup use their own qubits. They are using different types of qubits. For example, there is a company called IonQ in US that uses trap balance. Okay. So depending on qubits, sometimes they have some advantages, sometimes they have disadvantages. Depending on the purpose of the quantum system, they use different qubits. So here is the mathematical notation for quantum bit. Okay. So a quantum bit is written by using the fate notation. For example, this is called fate 0. This was introduced by Dirac. And a generic quantum state style is a superposition of 0 and 1, where 0 and 1 are called basis states. For example, if you are taking photon as a qubit, 0 corresponds to horizontal polarization and 1 corresponds to vertical polarization. And then these coefficients A and B are complex numbers. And you can also write this generic quantum state as a vector with the first element corresponding to the coefficient of 0 and the second element corresponding to the coefficient of second basis state. Okay. So in this way, we can actually write all quantum states as vectors. Okay. And then once you have quantum state, if someone wants to know what is the state of the quantum qubit, so one has to do measurement. Okay. Essentially, measurements are to sending photons to some photonic device, okay, which have some filters. They are essentially called polarization filters, and those filters they have certain axes, so either horizontal axis or vertical axis, and so on. So if you send a photon to a measurement device, you will get horizontal polarization with probability minus of x squared, and vertical polarization with probability minus of b squared. Okay, so this is what observed in labs, and it is not known why this happens when you are sending quantum-based photons to photonic devices. Now we can extend the property of notion of single qubit quantum state to multi-qubit quantum states. Essentially, multi-qubit quantum states they define the joint property of multiple qubits. Okay. For example, if you are taking 10 photons, you need 10 qubit quantum state. So now, for example, here for a 2 qubit quantum state side, we need a superposition of 4 basis states 0, 0, 0, 1, 1, 0, and 1, 1. And we have different coefficients. Again, if you take models of these coefficients squares, and then it is something it should come out. Okay. And in this way, we can also define a generic L-qubit quantum state, which will have 2 power n basis states. Okay. And also, these basis states need not be 0s to 1. We can actually have any orthonormal sets. Okay. Now, if you take a M-qubit quantum state, okay, particularly if M is 300, okay, the number of basis states that will be included in the superpositions are equal to 2 power 300. Okay. So now if you take classical computer, even if you have one classical state to each basis, you would require 2 power 300 classical states. Okay. Even if each of those classical states correspond to an atom, then the total number of atoms that we have in the universe, which is 10 power 82, is still less than 2 power 300. So therefore, we cannot even write a 300 qubit quantum state precisely in a classical computer. Okay. So this is the reason why why Richard Feynman said that we cannot necessarily characterize behavior of small particles in classical computers. On top of this, their quantum bits have some other properties like all quantum operators are unity operators and so on, which are not there for classical bits. So now an important property of quantum information is an entanglement. Okay. So entanglement is essentially is the notion of having strong correlations among qubits of a multi-qubit quantum state. So we do not have such strong correlations among classical bits. We only have a probabilistic correlation, which means that we have two random variables. We can compute what the joint distribution, what is the covariance, correlation coefficients, and all. There are much weaker correlations among classical bits. So here quantum bits essentially they are superposition of different quantum states. Okay. And now, for example, this is a particular 2-qubit quantum state. This quantum state has very strongly coupled qubits. 2 qubits are there, they are very strongly coupled. And what this equation says that we cannot write this quantum state as a product of 2 individual qubits, meaning that we cannot have 2 qubits that are behaving independent of each other. So if you substitute any values A, B, C, and D, you cannot get this left-hand equation. Okay. So, for example, you have entangled qubits. You need to talk about them with the jointly. Okay. So, for example, if you measure this quantum state, both the qubits will have 0, 0 state, or both the qubits will have 1, 1 state. So, there will be some synchronization among qubits when you measure them. So, because of this property, you can use this type of entanglements for various applications in cryptography, security, and so on. Okay. And then, as I explained, there is no counterpart in classical mechanics. Okay. And in quantum technology, most of the applications they require distribution of these type of entanglements. Even in quantum computing, quantum networking, and so on. Okay. Even in quantum communications and so on. Okay. So now in quantum networking, mostly we investigate how to distribute these type of entanglements in quantum networks. And sometimes these entanglements we have noise. So they may not have required properties. So we try to distribute entanglements that have desired properties. Okay. So now, how do we want to distribute entanglements? For example, here is a simple line network with two nodes. So we have A and B. We want to distribute a 2-qubit entanglement 5 place. Okay. In such a way that user A has 1 qubit and user B has 7 qubit of the same entanglement. Okay. So now user A and B can use these 2 qubits for different applications. And in quantum networks, generally our goal is to distribute multi-qubit entanglements to multiple users that are connected to the network in such a way that every user gets 1 qubit of that multi-qubit entanglement. Okay. Now, suppose there are any users which are connected to a network. If you have to create an qubit entanglement, each user should get 1 qubit of this entanglement. Okay, so as I just introduced entanglement, now let us look at what are the applications of this entanglement. So one of the most important applications is quantum communication. So we have a operation called Thirupathaiah. Okay, if we have an entanglement distributed between 2 users A and B, for example, here this is the entanglement 5 ways, and assume that this entanglement has 2 qubits, and the first qubit is located at A, which is denoted by QA, and the second qubit is located at B, which is denoted by QB. Okay. Now we have a data qubit B at user A, and here user A has 2 qubits B and QA. You can apply some operations on these 2 qubits, and some quantum operations. And those operations result in some different outcomes. Based on those outcomes, this user sends some classical bits to B. Okay. And based on these received classical bits, user B applies some local operations on its qubit. And then what happens? The state of this local qubit changes to data qubit B, which was available at A in the beginning. So here there is no physical transmission of quantum states. So at the end of this protocol, data qubit B gets destroyed at A and it gets recreated at B. Okay. So here the transmission of bits happens only through classical internet, which is classical bits. So that way in future, if we will develop quantum internet, we need classical internet to send all required control information. So what gate operations to apply, what is the measurement result, and so on. Everything will be exchanged over classical internet. Okay. So why it is important? What is the importance of teleportation in quantum computation? Suppose we have two users A and B. Can we do direct transmission of qubits? Why are we using teleportation? We're using entanglement. Suppose we have a qubit here, and if we send a photon from A to B, the probability of successfully transmitting photon to B actually decreases exponentially with the length of the channel. This photon goes through some attenuation inside the fiber optic channel, and the probability of successfully sending it decreases with the length of the channel. Okay, so this is a major drawback for sending directly quantum bits over fiber optic channel. Now, in practice, the length of the fiber optic channel should be less than 100 kilometers. Then only we can send a photon with some decent probability. Okay. If it is more than 100 kilometers, it becomes very difficult to send a bit from one node to another. Okay. So there is also another challenge, which is a no cloning theorem, which says that if we place some repeater in the middle, if the repeater doesn't know what is the state of the actual qubit we send, it cannot actually create multiple copies. It cannot copy and create multiple copies. But in classical communication, we use relays, which can actually receive weak signals and they can create multiple copies, they can amplify them and so on. In quantum technology, we cannot have this advantage. Okay. So because of these two challenges, it becomes very difficult to send qubits between two distant nodes, particularly when their distance is more than 100 kilometers. Okay. So that is where we can actually use teleportation. Okay. So suppose if due to some reason, somehow you create an entanglement between A and B, if the distance could be 1000 kilometers, 500 kilometers, 2000 kilometers. We can apply teleportation to send a qubit from A to B. Okay. For example, China's satellite experiment, they also did an experiment where they could create an entanglement when the distance is up to 1400 kilometers. So when you have 1400 kilometers, they can apply teleportation if you have an entanglement between sender and receiver. Okay. So there is also another important application of entanglement, which is distributed quantum computing. Okay. Most of the practical quantum processing units which are under development, they actually can have only up to hundreds of qubits. Maybe they can only have like 1000, 500, 300, 400. Okay. Because there are some practical challenges. Okay. For example, they require some cooling stations which will become very large if the number of qubits stored in QPUs increases. Okay. So and also there are some interference issues if you place many fiber optic channels inside a single CPU. Okay. So because of these reasons, practical QPUs can only have hundreds of qubits. But most of the important applications where we see that quantum has an advantage over classical technology, we need millions of qubits. Okay, so and then we cannot prepare some QPUs which will have millions of qubits. Okay, so then the only hope is to actually take several smaller QPUs and connect them to a quantum network, and then combine their resources and their capabilities to solve bigger problems. Okay. For example, if you are given with some big computational problem, you can break that problem into 4 subproblems and allocate each of those subproblems to one of these QPUs, and then you can exchange results of these QPUs through teleportation and combine the results at some particular QPU. Okay. So in that way, we can solve bigger problems.
The communication between the QPUs will be a classical communication, right? Not a quantum one.
If the final result is quantum state, then if you have to combine quantum states, then you need to do teleportation. And if the distance is small, you can do direct transmission. But sometimes sending quantum state directly to fiber optic channels is also risky. So because there will be some interference, if there are so many wires, fiber optic cables, there will be some interference across fiber optic cables. So generally, it is better to apply teleportation, even if the distance is smaller here. Okay. So for classical bits, we need classical channel. But if you have to say quantum bits, then you need teleportation. For that, you need to distribute entanglements between different QPUs on this network. Okay. And another advantage is that you can apply gates, quantum gates remotely. For example, if there is a qubit in QP1 and if there is another qubit in QPU2, if you have an entanglement between QP1 and QP2, you can apply some remote gates using that entanglement. So you can apply distributed quantum gates, which actually further helps in speeding up our quantum computation. So the main motivation for developing quantum networking is actually quantum computation. So people are now talking about developing high performance computing architectures, quantum computing architectures, like developing like quantum data centers where we connect several quantum computers using a quantum network. So we need to develop what are the efficient quantum networking algorithms to connect these QPUs. And then there are other applications like quantum key distribution, error correction, sensing, and so on, which I am not going to talk about. But the most important applications is quantum computation and quantum communications. The moment there are two nodes, located far away from each other, then you need teleportation. Okay. So in future, for example, satellites are going to play a major role in developing quantum internet. Why? Because in the space, after 500 kilometers, it is completely vacuum. There is not much noise. So photon can travel over long distances. That's why China's experiment was able to distribute quantum states over 1200 kilometers. Okay. So if you have to connect to quantum nodes located in different continents or different countries, we must use satellites in the area of quantum technologies.
So during teleportation, can you teleport as many times as you can?
Yeah, you need every time you need one entanglement. So entanglement you can't do in that process. So you can't teleport one more qubit, you need another entanglement in those users. So ultimately you need to create entanglements at faster rates. If you have high faster rates and entanglement, then you can teleport more number of qubits. Okay. So this is the motivation for quantum networking. And how do we create entanglements between two neighboring nodes on a quantum network? Okay. So here is user A and user B. Suppose if their distance is sufficiently small, you can actually do direct transmission. So you can prepare two entangled qubits. You can keep one entangled qubit here and you can send another qubit to B. Okay. But if the distance is a little bit larger, then you need to create two entanglements, one entanglement A and another entanglement B. And for this purpose, we use something called communication qubits. Okay. So what is this communication qubit? These are essentially some atoms of some materials. For example, the trap ions, they excite them, they actually break into entangled qubits. Okay. So if you excite the communication qubit, actually breaks into two entangled particles. And one of those particles is another communication qubit, and another particle is a photon. And these two communication qubit and photons are entangled with each other. And then you can transfer this photon to another device which is placed in the middle to a fiber optic channel. Okay. So in this case, at user A, we excite a communication qubit. We place a communication qubit at user A, but we send the photon towards this bell state analyzer, which is a device where we apply this bell state measurement. Okay. And similarly, user B also transfers one of those entangled photons towards this device. And these two photons, they interfere with each other. And then finally what happens is that the joint state of communication qubit placed at A and other communication qubit placed at B will be having an entanglement by the end of this operation. So this is called, essentially here we actually teleport the state of this photon to B. So therefore these communication qubit and this communication qubit, they will be entangled with each other. Now, how this interference happens with this bell-shaped analyzer in the middle, that interference has to happen in certain way, and it happens only with some probability. That's why this bell-shaped measurement or entanglement swapping that we do with switches, it succeeds only with some probability. Okay. So here is the process. Like for example, we have two hop network. So here is the user 1 and switch. So we create entanglement using the previous method that I just explained. And we create another entanglement, red colored entanglement between user 2 and switch. Now the switch has to apply this bell state measurement or entanglement swapping. And then it merges these two entanglements. And what happens is that we get an entanglement between user 1 and 2. Okay. So this is how we can create entanglement between remote nodes if their distance is large. Okay. Now here is a network. Now Suppose we have a quantum network where we have different devices, repeaters and switches. Okay. So switch is essentially a device which is connected to more than 2 links. Repeater is connected to only 2 links. Now we have created an entanglement between this link and this link. Okay. By creating an entanglement here and then we transfer our one to here and similarly here. Okay. So now we can create different entanglements. For example, here, for example, if you want to create an entanglement between this guy and this guy, we need to use this entanglement and this entanglement. And for that, this switch applies this entanglement swapping operations using these 2 qubits. And which finally leads to creation of an entanglement between this user and this quantum computer. And similarly, here you want to create this entanglement between this user and this quantum computer. We need to use entanglements of 3 links, 4 links, this link, this link, this link, and this link. So now quantum networking is essentially path selection. If you want to create an entanglement between different user base, you need to select appropriate paths. Okay. And then you need to use research of these switches repeaters effectively. Okay. And recently there have been some important works which showed the importance of quantum networking. For example, Cisco has come up with a work on quantum data center infrastructure. Essentially, they showed that quantum processing units are going to have computations in terms of network qubits. Therefore, you need to build a quantum network to find those QPUs. And particularly, you need to have quantum data structure infrastructure if you want to solve bigger computational problems. Okay. And similarly, they have also come up with some quantum networking chip where they can create entanglements for different outputs. And then there are other works which showed quantum networking applications like error and so on. Okay. So that's why quantum networking is very important if you want to scale up quantum computation as well. Okay. So now we will see the differences between classical switch and quantum switch. So here is a classical switch. Okay. So in the classical switch we have input ports and output ports. At every input ports we receive packets which needs to be transferred to one of those output ports. For example, this guy has to be transferred to the first output port, and this guy has to be this packet needs to be transferred to the output port again. Okay. Now here the goal is to how to transfer packet from input ports to output ports so that these queues are stable. These packet queues are stable. Okay. And people have come up with a policy called maximum scheduling algorithms. Essentially, QIJ is a queue size for packets which are arriving at input port I and output port J. Then we need to select a schedule here, which indicates the number of packets we can transfer from input port to output ports, which is denoted by Nij. And essentially, in your task based on initialized queues, we need to select a schedule here that maximizes this function. Okay, that is called maximum scheduling policy. And in this paper, they have shown that such a maximum policy achieves throughput optimality, meaning that all feasible rate vectors can be stabilized under this scheme. Okay. So now we want to develop such a scheme even for quantum switches. Because if you want to create entanglements at higher rates, you need quantum switches that perform matches at faster rates. Okay. And also those matches should be effective, they should be useful. Okay. So what is quantum switch now? So quantum switch essentially on one side you get Link-Level entanglements between user and the switch. On the other side, application generate requests. Okay. So now we want to match Link-Level entanglements to requests so that requests are stable. Okay. So here these mapping operations that we apply at switches, they will circle more with some probabilities. And Link-Level entanglements also recover with that, and there is a limited number to store them also. For example, in this case, each link can store only up to 2 Link-Level entanglements. Okay. And when we are doing scheduling, so we have 2 cycles or 2 phases. In the first phase, we need to actually select a matching, which links are matched to which request. Okay. And then the switch has to apply swapping operations. Swapping operations are essentially some quantum operations, which will substitute with some probabilities. And if these swapping operations are successful, then we get entanglement for desired user base. Okay. Sorry.
So you said
the B values memory, right? Is
Yeah.
there any constraint on memory that you know you
Yeah. So in practice, because the quantum memories are expensive, so in practice, users and switches, they will have limited number of devices. They are still under development, and also they do not have good properties. If you store them, there is a high chance that you will lose qubits. Okay. So here are some parameters. For example, type I requests are assumed to arrive at rate lambda, and for type I request we need NR to be entanglements. So okay, and Link-Level Entanglements for type L arrive to rate lambda L, and every link can store up to B Link-Level Entanglements. And swapping operations that we apply for type I request, they succeed with probability gamma. And then at link L, all unused link-level entanglements, they recover with probability DL in each time slot. Okay. So by the end of the time slot, we will have certain unused link-level entanglements, and they will disappear with some probabilities, and that probability is DL for link L. So here are the dynamics. So we have queue size per request R at the beginning of T plus 1. And these are the queue size at the beginning of time T, and these are the requests that are solved. Okay, that are solved, and then these are the new requests arrive. Okay, and here NR of T indicates how many type of requests are actually selected for swapping. And out of NR of T, only some of them is succeed. Each succeed with probability gamma. Okay, so N hat R of T indicates what are the actually solved requests. Okay, so this is the dynamics of queue size of request. Okay. Now we look at the dynamics of queue size of link L. Okay. In this case, we have ZL of T, which indicates the number of link-level entanglements available at the beginning of time slot T. Okay. Now for YL of T, I will explain what it is. So we have ZL of T minus 1 link-level entanglements at the beginning of time slot T minus 1. Plus newly some link-level entanglements have arrived, AL of T. And this has to be bounded by B because the quantum memory size is B. So, okay. So we apply some operation here so that the value is always less than B. And out of these link-level entanglements which are available, we use sigma L of T. Okay. So sigma L of T. And then YL of T are the ones which are left over by the end of time slot T. Okay. Out of these YL of T, some of them disappear due to decoherence. Okay. So ZL of T essentially indicates what is the number of link-level entanglements that are actually present at the end of time slot T. Okay. So this is the evaluation of two different queues for link-level entanglements and requests.
Sigma and NR related.
Yes.
Otherwise,
yeah. So the sigma and L, they will select according to the scheduling scheme.
matching.
Yeah. So we need to select sigma and NR in each time slot carefully so that the request queues are safe. So here are some related works. Okay. So the first work on quantum speech is this one, where they have only considered one-sided queues. They did not consider the applications. They only considered the link-level entanglements, and then they applied something called old link-level entanglements first. Suppose if all link-level entanglements are available, you cannot really match it. Then you need to actually prefer the one which has arrived first. And they did not consider any applications. And in the next work, we have considered a simple quantum switch model which by considering application requests. Okay. However, in this case, we assume that qubits, link-level entanglements, have very small lifetime, meaning that they expire at the end of one time slot. They arrive and then they immediately should be matched. Otherwise, they will disappear. Okay. That is the simplest model. And this has some connection to classical networking scenario also. So another two techniques come from classical networking directly. Okay. And in the next work, they have considered the scenario where link-level entanglements can survive for more than one time slot, but they considered only like two applications. Two applications and three links. And their two techniques are extended to generic quantum switch model, which we have considered in this work. Okay. So now we will show can we apply max weight policy to our set. for a quantum scheme, we choose the Maxwell policy. Suppose if you choose a Maxwell policy, essentially what it should do, we want to stabilize request queues. So we need to schedule a number of request queues, request officer that we select for service. And sigma indicates how many link-level entanglements we are using for each link. Okay. And we need to select again such that this sum is maximum. That is what Maxwell policy is. Okay. Now it is easy to implement. Why? Because we do not need to use any system parameters. We just need to use dynamic Q values. Therefore, we do not need to use any IO rates. Okay, so this is an advantage of Maxwell policy. Now I will show that this scheme is not optimal for quantum systems. Okay. Here is a counter example. So what we understood from this work is that in Maxwell type schemes have maximum capacity for quantum. The answer is no. We need new type of algorithms. And can we find a throughput optimal scheme for quantum system? And we are showing this work that yes, we can find. And we need to actually use NDPs to design optimal scheduling algorithms for quantum switches. Okay. So here is a counter example. Suppose that we divide time into different segments where each segment has 3 time slots. Okay. So in first time slot, one link-level entanglement appears here in this link. Okay. In the second time slot, one link-level entanglement appears here, and in third time slot, one link-level entanglement appears here. Okay. And then it repeats in every time segment. In the first time slot, we get one entanglement, one link-level entanglement in the first user. Firstly, and in the second time slot, you get the second link-level entanglements. In third slot, you get third link-level entanglements. Okay. And this request, the first type of request, they use only link-level entanglements of first link. Okay, so this is a simplified model. This is not the exact model that we consider. Okay, and the second type of request, they use only second links entanglements. And third type of request, they require all the links entanglements, one from each link. Okay, and furthermore, these links entanglements they can survive for 2 more time slots. If it arrives in the first time slot, it can last up to the third time slot. And this link entanglement, it can last up to third time slot. They have only two lifetime. Whereas this guy has only one time slot. If it arrives in third time slot, it's used in third time slot. Now, if you are applying max weight, because in the first time slot we see only this link-level entanglement, so immediately we will start correct on request. Because max weight algorithm is ready algorithm, it may have this. So it sees this link entanglement, therefore it immediately matches to type 1 request. And the next it goes to the next time slot and then it sees this link-level entanglement, therefore it immediately matches to the second request. Okay. And then for type 3 request, it will solve type 3 request only if these links entanglements are available. But they will not be available because it will be immediately solved for other requests. Okay. And type 3 request will be solved only if there is no other request in these 2 queues. Okay. So now we have a constant and lambda 3. This is a stability constant for matrix. What it says that lambda 3, that is the arrival request rate of type 3 request, should be less than 1 minus lambda 1 minus times 1 minus lambda. It means that both the type of request should have empty queue sizes. Then only type 3 request can be solved. This is the capacity design for Maxwell scheme. But suppose if you delay scheduling decisions, for example, instead of surveying the entire first slot, second slot, suppose if you make scheduling always in third time slot, then you can make better decisions. For example, you can look at type 3 request, type 2 request, type 1 request. Based on the queue sizes, you can make your scheduling decision optimal. Okay. So the total capacity design is generally this one. For example, this corresponds to the fact that type 3 request uses both link 1 and link 3. Okay. So this gives that leads to a condition like this. Okay. And what we show that for lambda, suppose if you take lambda equal to 0.4 per hour, then this condition is not satisfied. So therefore, Maxwell scheme is unstable for this particular context. And we will show that our scheme is stable for this condition as well. Okay. And by using a counter example, we argue that Maxwell scheme is not throughput optimal when link-level entanglements have probabilistic decoherence. Okay. So here are some numerical results. For example, we have plotted Q size. Okay. So our scheme is our scheme, and max weight is this curve. And if you see here, the Q size of the system increases monotonically under max weight scheme. Whereas in our case, in our scheme, the Q size becomes stable. They become final. So therefore, we have found a counter example where max weight scheme is not optimal. So therefore, the macro scheme is not good optimal for performance. Next, we will see how we have come up with our scheduling algorithm. Okay, so we use a Lyapunov drift function to come up with this idea. Okay, so because link-level entanglements are expiring with some probabilities in every test slide, we observe that there will be some two time scale separation between queues and link-level entanglements. The reason is that these link-level entanglements, they will have a lot of dynamics before you see significant changes on these request queues. Because in every slot, some unused link-level entanglements will expire. So you will see a lot of dynamics in the system. Therefore, this process reaches to the station very quickly. Okay. So from this system point of view, this system is stable, is constant, it's not changing. And whereas from this system point of view, this system has already reached stationary. Okay. So this is a typical idea in queuing systems. So using that idea, we can write Lyapunov, take a Lyapunov function like this, and using fluid link analysis, the differential equation of the fluid link will be of this form, where in this case the departure process of the request queues will have expected departure, assuming that the left process has already reached stationary. Okay, so this is the expectation with respect to the stationary distribution. And if you select NR pi according to the policy pi, then you get this average number of departures. Okay, so this is a fluid limit equation. Now, in order to stabilize the request queues, we need to actually maximize this departure term. Okay, so that is for every queue. Okay, this we need to select it twice such that this negative term is maximized. Okay, so that is our scheduling scheme. So we have to find a policy pi for the based on the request queues QR, such that we get this expected reward is maximized on the given policy pi. Okay.
There's no one question. Why do you want to do this? Why not just go with directly? That your request for entanglement comes, and how long does it wait depends on the queue itself. And you're anyways trying to do an MDP to maximize the queue, so you might as well solve the original MDP, which is sort of related to the waiting time itself.
So here this is not exactly waiting time.
I know. Yeah, I will just go ahead and minimize the average queue length itself.
Yeah.
That is actually gonna make sure this happens already. You minimize the queue length, then you're gonna minimize, like the first of all, it's not stable, it's not right? So yeah, the proxy problem, right? You can actually solve the original problem, which will be not order more complex than what you do right now.
Yeah. So you need to find for every queue, you need to make a negative drift.
I will just make sure I minimize the queue itself, right? So what is your right thing to do? It's like give me a matching such that my sum of the queues becomes small. That's it. So you're writing QRT, gamma, and R pi, right? I just want my goal is that max pi. I don't know what U pi is. The summation of QR itself is. I will not, worry about NR pi itself, right?
So this is the expected departure time. So
yeah,
you need to select.
I don't need to do that. I can just try to minimize the queue itself, right? Anyway, we can talk this up.
Yeah. Okay. So we are interested in throughput optimality. Okay. So naturally, because the link process is fast is running at fast time scale, so we will have two time scale separation, and this is the fluid limit equation. Okay. And now basically we need to find for given queue, it corresponds to the request queue size. We need to find a policy that maximizes this expected reward. for the link process. Okay, and we denote this optimal policy by 5-star Q. Okay, and essentially we solve this optimal policy using Bellman equations. Okay, so this Bellman equation is correspond to average reward MVPs, and essentially we will find this 5-star Q by which maximize this star. Okay, and once we find MVP solutions for each request queue size. Now we need to use those policies to stochastic system. How do we make scheduling systems for a given finite system? Okay. So now we divide time t into time segments, where each time segment has a length tau. Okay. So we will choose this tau value very carefully so that we get the three equation that we derive. Okay. And within this tau, at the beginning of each time t, which is divisible by tau, we look at what is the queue size of the request process. We take this Q of t, and then we implement the policy 5-star of Q of t. Okay, from the previous slide. So we take 5-star of Q, which is optimal scheme here, and basically here we take that 5-star of Q of t by just looking at the queue size at the beginning of this segment, and then we run this policy during this interval t to t plus tau minus 1. Okay, so 5-star of Q of t will be retained as a scheduling scheme for a interval of length tau. Okay, and this scheme is called R policy, which is essentially average reward entanglement policy. Okay, and here also we do not need arrival rates to stabilize system. Basically, we just use Q sizes. Do not use any system parameters. Okay, so this is our scheme. And we then characterize capacity region. What is the stability region for the quantum switch? Okay. Suppose that if there is a request rate and the request rate is stable and some speed, then the expected departure rate of the system should be larger than the expected rate of arrival rate. Okay. So this is the lambda should be strictly smaller than the expected departure rate. Now, based on that idea, we can actually consider a policy that focuses states based on the Link-Level process, and that Link-Level process is actually agnostic to the request queues. Okay, and we want to consider a policy such that the expected departure rate is larger than the expected arrival rate. Okay, so this is a necessary condition to this table under any scheduling scheme. And then we will have a sufficient condition. Suppose we have a lambda satisfying this term. Okay. So we will consider a static policy, which is that suppose if we see Z and Link-Level entanglements on the state, then we will take this probability to select a schedule. So here what it says that if you have a state Z and Link-Level process, with probability P of sigma L given Z, we will select the schedule sigma L. Okay. So this is and then we will run the system on the Link-Level process according to this scheduling scheme. And then whenever we have selected it, we will have NR request selected for service, and out of them NR gamma will be successful on average. Okay, and whenever some requests are whenever we match entanglement swapping successfully, based on the available request queues, we will solve those requests. Okay, if the number of successfully created entanglements is more than the number of available requests, we will just throw away and request certain Link-Level certain entanglement that we generated. Okay. So here the idea is that we have to always focus on service process, which is a Link-Level scheme, and that the service process should generate with entanglements at rate that is greater than the request rate. Okay. So now what is the policy that maximizes the service process? So that is agnostic to the request queue. So this is how we derive the capacity region. Okay. And then we show that our policies are asymptotically optimal. Why? So what is asymptotic optimality? So here we have chosen tau to be a function of C. Okay. That which is that tau C is equal to log C whole square. Okay. Therefore, here these are sequence of policies which are the functions of C. Okay. And as C goes to infinite, we will show that these sequence of policies converge to pi, which corresponds to the fluid limit equation that I showed earlier. So asymptotically, we go to the two times scale separation and fluid limit equations as we goes to infinite. Okay. And in this system, we observe that the mixing time of the link process is small, sufficiently small. So it is only the order of log C. Okay. So here we consider that quickly link-level process converges to the stationary, and then the allocation of link-level entanglements for certain requests happens according to the stationary distribution of the link-level process. See, I will tell C which is the normalized parameter in the fluid limit analysis. Okay. So what is the definition of asymptotic optimality? So a set of policies, phi C, where C is the parameter of these policies, are said to be asymptotically optimal if for every epsilon greater than 0, there exists some constant C epsilon such that for all C greater than equal to C epsilon, the policy phi C is positively correct for all lambda belongs to C epsilon. That's C epsilon. So what is C epsilon? C epsilon we consider all the arrival rate, feasible arrival rates that are within a distance of epsilon from the boundary points. Okay, so suppose if the epsilon converges toward 0, then we reach the boundary point which is the capacity region. Okay. Now as see epsilon decreases, we will have to increase C epsilon, this small C epsilon. So these are asymptotically optimal. Okay. So here is the C parameter. Essentially, this is a normalized process. We take the request queues, we increase the time value, and then normalize the queuing process by C. And similarly for link-level entanglements, we take normalized by C and a scale of time by C. Okay. And as C goes to infinity, what happens because link-level entanglements have finite value. So this Z bar of T in the fluid limit is 0. Okay. However, this fluid limit, the convergence of this process goes to some equation, deterministic equation, which follows the differential equation that I derived earlier, which I have shown earlier. Okay. So in this proof, we first need to show that this queuing process is tight, which means that for every sequence of process, there is some convergence of sequence. Okay. And then we do two times scale separation, using which we showed what are the fluid limit equations of the limiting process. Okay. And after that, we show that the fluid limit is stable and under our R policies. Okay. And it is the fluid limit stability of the system. We actually show that even stochastic systems are stable. Okay. Meaning that using multiplicative Foster-Lambda theorem, we show asymptotic optimality. That is that if C becomes larger and larger, the stability region converges towards the capacity region. For every epsilon, we find some C epsilon, which can be used to achieve the stability of the system. Okay. So this is how we prove asymptotic optimality of our sequence of policies. Okay. So to conclude, we understood how Maxwell's scheme cannot help us to make scheduling decisions optimally in quantum systems. And we then proposed an optimal scheduling algorithm by solving average probabilities. Okay. And we also characterized the capacity region of the six quantum switches and showed that our policy achieves asymptotic optimality. Okay. Meaning that tau parameter, which is a function of C, has to become larger and larger in order to increase the stability region. Okay. And in future work, we would like to extend our proof to the scenario where link-level entanglements have boundary latent. Okay, so here they follow the Bernoulli process. They every time that they disappear with some probabilities, but in practice they actually expire within some time limit. So we want to extend our proof to that in our general version. And then in future we would like to develop scheduling algorithms for quantum networks. Here we focus only on quantum space. Now we want to extend this type of works to quantum networks. And furthermore, we are now looking at optimal algorithms. There is also importance to look at low complexity algorithms. For example, Maxwell scheduling type of algorithms have significant complexity. And then how do we schedule these? How do we solve these empirical problems with low time complexity and so on? So these are future works that we would like to extend. And this work was appeared at Symmetrics recently, and there is a paper that is available in archive. So I will stop here. Thank you.
Thank you, Professor, for a wonderful talk. So I would request audience to have ask questions if there are any.
we ask a lot of questions.
Okay. In the interest of time, and we'll end this session now. If you still want to talk with Professor or connect with him, please feel free to do so by having a cup of tea at our coffee. Thank you all.